Hi, ladies and gentlemen. Let me wholeheartedly welcome you to the new session on ECT 204 signals and systems. Today, we see how LTI systems or discrete LTI systems are modeled with difference equations. This is a 15th session. So first, this speech is organized into your learning outcomes, then LTI systems or discrete LTI systems modeled as difference equations. Then we will see another major classification of discrete LTI systems. That is, the first class is the finite impulse response or FIR systems, and the second is the infinite impulse response or IIR systems, and then the summary of understanding. The learning outcomes of this session are: first, you will apply difference equations to model discrete LTI systems. Then you will learn the classification of discrete LTI systems into finite impulse response or FIR and infinite impulse response or IIR filters. Then you will understand the general block diagrams of FIR and IIR filters. Discrete LTI systems, they are modeled as difference equations. Let us consider a simple example of an LTI system with Hn, the impulse response, equal to alpha raised to n un, and say the input is xn. So output of this system yn will be the convolution between this hn and xn. That will be since it is there is a un percent in this summation is from k is from 0 to infinity alpha raised to k xn minus k. This is our self same convolution equation. So if I take the first term, that is with k equal to 0, that is alpha raised to 0 is a 1 times xn, plus k equal to 1 to infinity alpha raised to k xn minus k. Now you can see that this is nothing but xn plus this is alpha xn minus 1 plus alpha square xn minus 2, etc. So this is nothing but xn plus alpha times yn minus 1. That is, if I put n equal to n minus 1 in this equation, that results in this. So this is nothing but xn plus alpha yn minus 1. Now you can see that in this system, the output depends not only on the present input, it depends on the past output also. So that means in this system, the past output should be stored somewhere, or in other words, you can see that there is a feedback connection from the output to the input. Okay. Now this can be graphically put like this. This is my input xn, and here there's a summation. So this is my output yn. This yn, there's a delay element here. This is yn is fed back to the input through a delay element. So here it is a yn minus 1. So then there is a multiplication by alpha, so it becomes alpha yn minus 1. So it is xn plus yn minus alpha yn minus 1 becomes my yn. That is the system. Now you can see that there is a feedback loop in this system. There is a loop from output to the input. There is a connection from output to the input. Now this, whatever we have seen, is a special case of the general linear constant coefficient difference equation modeled as, say, yn equal to k from 0 to m, say beta k xn minus k, okay, plus k equal to 1 to n, say alpha k yn minus k. These constants alpha k and beta k, they define the system. Actually, finding this alpha k and beta k, these constants are the design of this system. Now you can see that this has got two terms. So one is the first term. You can see that this depends on the present and past input. With k equal to 0, it depends. It is beta 0 xn, that is a present input. And for k equal, for values from k equal to 1 to m, that depends on the past inputs. So this the first term that defines the dependence of output on the present input and the past inputs. Whereas if you look into this term, this term shows the dependence of the present output on past outputs. So you can see that this summation is from k equal to 1 to n, because k equal to 0 corresponds to yn. So this is some alpha 1 yn minus 1 plus alpha 2 yn minus 2 plus etc. to n times. So here in this, it depends on n past outputs and present input and m past inputs. So the first time this shows the dependence on the present and the past inputs. The second time this shows the dependence on the past outputs. So this alpha k and beta k decides the extent of this dependence, and finding this alpha k and beta k, that is a design of the discrete system. Now, if all alpha k values are zeros, that is, then the second time will not be present. If alpha k is 0 for every k, then the second time will not be present, and you can see that the output depends on present inputs and past inputs, and not on any past outputs. So it's a non-recursive system. Okay. Otherwise, it's a recursive system. If alpha k are non-zero, then it's a recursive kind of system. For a non-recursive system, you have yn equal to k from 0 to m, beta k, xn minus k. Now, you can see, suppose this xn is a delta n, that is, if I am launching an impulse, a unit impulse into the system, the response will be, hn will be k from 0 to m, beta k, delta n minus k. So you can see that this is finite in duration. This hn is finite in duration. It can have, say, m plus 1 values. Okay, its in length, it is finite in length. Its length cannot exceed m plus 1. Okay. So such a system is called a finite impulse response system. That is, the length of the impulse response is finite. It does not depend on any past outputs. It depends only on inputs and past inputs values. Here the length of bk or hn, that is finite. So this is called an FIR system, or a finite impulse response system. Now, in FIR systems, the output depends only on the input and its previous values, and not on any past output values. So there cannot be any feedback loop in the system. Now, there are only forward signal paths in FIR system. If I put it graphically, this is my input xn, this is multiplied by beta 0 here, then it is delayed by 1 unit, so here you get xn minus 1, that is multiplied by beta 1, then xn minus 1 is delayed again, that is delta n xn minus 2, that is delayed by beta 2, etc. It comes to beta m. Okay. So you can see that it's a sequence of or a series of multiplications and additions. So this multiplications and addition result in my finite impulse response system yn. Now you can see that there are only forward paths in the signal. There cannot be any backward path or any feedback path in the system. So if I launch an impulse here, either it can take a path like this and reach at the output at n equal to 0, or it can take a path like this and reach the output at n equal to 1, or it can take a path like this and reach at n equal to 2. Or else, suppose if I have m delays here, it can have m delays to reach output yn. But so that means the length of the impulse response is finite. It is m. So this is how I picture an FIR system. Now the second class is the general class of systems, that is called the infinite impulse response system. That is a general system with a non-zero alpha k and beta k is an infinite impulse response type system. Its impulse response is infinite duration. This system depends on the present and past input values as well as the past output values also. So there must be at least one feedback signal path in this system. If you look into this model, you can see that this is a forward path, this is my input xn, that is multiplied by beta 0 and comes here. It is delayed by 1 unit and multiplied by beta 1 here. And here I have m delays, then there's a multiplication by beta m. This is my FIR system, or this is my forward system. Now you have a backward system also, that is the dependence on yn minus 1, yn minus 2, etc. Suppose there are n delays here. Either the signal will come here, yn comes here, this is delayed by 1 unit, that is yn minus 1, that is multiplied by alpha 1 and added here. This yn minus 1 is delayed by 1 unit, yn minus 2 and added here. Finally, there is an n delays here, this is yn minus n, that is multiplied by alpha n and added here. Now you can see that there are many feedback paths in this system. So what can happen is, in the forward path there are only m paths. Okay, but in the reverse path, suppose I launch an impulse here, it can take a path here and reach at output, that is at n equal to 0 itself it can reach, or it can pass through this one and reach the output at n equal to 1, or it can take two revolutions in this, or you say it can traverse this path twice and reach at n equal to 2, or this impulse can remain this loop for say infinite instances. So you can expect, suppose I launch an impulse here, you can expect its response at any time, even at n equal to infinity. So that is why we say this filter is an IIR type filter. Now when you come to the summary of understanding, here you apply different equations to model discrete LTI systems. Then you learn this important classification of LTI systems into finite impulse response filter and infinite impulse response filter. Now in finite impulse response filter, the output yn depends only on the present input and the past inputs, and not on any output values, any past output values. So there cannot be any feedback loop in an FIR system. So that FIR system is an inherently stable system. And you have the second class, general class of systems, that is the infinite impulse response filter, where there is at least one feedback path. The IIR filter, that depends, the output depends on the present input, the past inputs, and also the past outputs also. So there is at least one feedback path from output to the input. So that makes the impulse response infinite in duration, because an impulse launched at n equal to 0 can remain in a feedback loop for infinite amount of time, ideally. And the impulse response is ideally, that is infinity. Now then you understood the general block diagram of FIR systems and IIR filters, and that is the end of this presentation. I thank you all.